Hello, tensor friends. This morning I was reading Carol's book on general relativity, and I kept reading these words, covariance and invariance, and I really started thinking about what's the difference in these two words. Now, this word covariance, this is not to be confused with a covariant vector component and a contravariant vector component. This is not what it means. This is used in the format of general covariance, which is what Einstein used to say that the laws of physics have to remain the same in no matter what coordinate system the observer is in. But I think I've been using these interchangeably, and they're actually not interchangeable. They're very nuanced in their relationship. Okay, so invariance means that a quantity or a law does not change at all under a specific transformation. So there's not a coordinate transform for an invariant. It's just invariant. It doesn't change no matter what you do. And covariance means that a quantity changes in a predictable, well-defined way under a transform. Okay, here's an example of invariance. In special relativity, the speed of light is a constant. It's invariant in any coordinate system, as is shown in this time dilation equation, right? So you have a Lorentz transform for the time of a person at rest versus the time of a person in motion traveling at a constant velocity. So there's a difference in their clocks, and it's given by this expression where the speed of light is the same for the person not moving and the person moving. So this is an invariant. There's no way to transform it between these two. It is the same. Okay. Uh, Now, what's an example of covariance? Okay, I'll just go through this real fast because that's the point is just to show the example. Okay, so we have a vector in two dimensions, Cartesian the coordinates. It has these components and the normal orthonormal basis, the orthonormal basis vectors. Okay, what is the magnitude of this vector? Well, it's 5, right? We all know how to do that. Now, I want to transform that to the coordinates r and theta using these well-known transforms. Okay, so I get this for r 5, and I get this many degrees and this many radians for the angle. Okay, now I have a VR component and a V theta component, but now I need these to be in terms of ER and E theta. Well, how do I do that? The way we always do in tensor calculus. You say the uh, the object in the unprimed the system is equal to the object in the prime the system via the Jacobian J I prime I. Okay, now what's that mean for us? So as an example, this would be EX, and here's X. That's my free index. X. My summation index is I prime. So in the first case it's R. The second case is theta. Now, what does this mean? What is JRX? Well, that's the partial R respect to X. This is the partial theta respect to X. Now, what are these things? Well, they're the partial derivative of a position vector with respect to R. This is the partial derivative of a position vector with respect to theta. So this is basically the multivariable chain rule, right? All right, so I'm not going to do the derivation because we've done it before, but here's the punchline. So here is EX expressed in R and theta. Here's EY expressed in R and theta. So I can plug this back in here and this back in here, there rather. I can crunch, and now I know what theta and R is. Right here they are. This is R and this is the theta. So I put all of that in everywhere, and I get this expression. I simplify it, and I wind up with this. Now, I want to know the magnitude of the vector now. It is totally in the coordinates of r and theta, okay? So how do I do that? Well, the first thing I do is square it. Now, we're going to get er dot er, that's 1, and e theta dot e theta is r squared. And we're going to get this. We know what r is. It's 5. We put that in, and we get approximately 5. There's some decimals out here. I don't care. The point is the magnitude of that vector is 5. So it is the same vector we started with, but it transposed in a predictable way using these derived transpose equations, okay? So that really is the difference between those two words. And I have been defining tensors as geometric objects that are invariant under coordinate transform. Well, that's not exactly right. If you want to get real nuanced about this, I should say tensors are geometric objects that transform in a predictable way. I think this is more responsible. All right. Anyway, I'll see you later.